So we know of 3 nuclear test explosions in North Korea in 2006, 2009, and 2013. But several papers have now been published claiming a 4th, very small nuclear test in North Korea in May 2010. Is that real or not? And my plan for this talk is to run through some background slides quite quickly, describing work done roughly in the first half of this year, and then to spend more time towards the end of my talk describing work done just in the last month, which has led us to reach a conclusion on what the event actually was. So this is work of 4 people, 3 of us at Columbia University, and an expert analyst in Europe, Karl Koch. So the story begins actually in the year 2011, when a distinguished radiochemist from Sweden kind of broke ranks and said, look, there's some very strange anomalies being observed, thank you, around North Korea. So I showed this graphic actually in the previous presentation here, so I'll just run through it. You're looking toward the southeast at the Korean peninsula, and in green Japan in the distance, and the 4 red dots describe the location of 4 stations which have anomalous radionuclide observations. And here they are, xenons, barium-140, lanthanum-140. And the interpretation of the author of a paper published in 2011 was that there must have been 1, possibly 2 small nuclear explosions in North Korea on specific dates. He says May 10, May 11 of 2010. So with a team of colleagues, here he said small, on the order of a few tens of tons. With colleagues at Columbia, I searched very carefully using the best openly available seismic data, using templates from the known nuclear explosions and cross-correlation methods as a kind of match field, looking on the days suggested by Lars Erik de Geer, and could find absolutely nothing. Specifically, the station we worked with was an open station in Manchuria, Manjang, at a distance of a bit less than 400 kilometers. And the conclusion we reached at that time from data like this, when you're dealing with events at the magnitude 2 level, that's comparable sometimes with the signal of a train going by or somebody jumping up and down in the next building. Very small signals, which mean that there are very many on a typical day. Here you say the quiet of nighttime and the relative noise in the background during daytime hours. And the conclusion that we reached 3 years ago was, to summarize, if anything had happened, we couldn't detect it, and so it would therefore have to be very small, less than about magnitude 2, to escape detection. 2 years go by. And early this year was published a paper with this very strongly stated title by 2 Chinese authors. The second author is actually a dual appointment. Lianxing Wen, whom I've known for 20 years, is a senior professor at the State University of New York in Binghamton, claiming, not on May the 10th or May the 11th, which are the days that my group had tested, but on the following day, a few minutes into May 12, had happened a seismic event, in other words, a confirming technology, originating signals from the North Korea nuclear test site. Using stations, as you see them here in red triangles in China, not openly available, not available to readers of the journal in which this claim was published, using a method of stacking cross correlations, and at about magnitude 1.5. So it was indeed too small to be seen at the great distance of the Mudanjiang station. And using a good method, and now this is the first of the discrimination graphics that I shall show. And the claim was that it was an explosion on the basis of a measurement, as you see on the y-axis, of the ratio between P waves, which are excited strongly by explosions, in the numerator, Pg, and in the denominator, Lg, that's a wave that is excited more strongly by earthquakes. So if that ratio is high, you would say this is probably from an explosion. If that ratio is low, you'd say it's probably from an earthquake. And the Chinese group had 3 earthquakes, which they show in black. They had at that time 2 nuclear explosions in North Korea, which they show in red. And they chose, with their problem event, which actually fell in the middle, to color it red and say it's a nuclear explosion. Going back to the set of stations available, first of all, in yellow triangles are data from a research project, which is openly available to anyone. And I was able also to get access to stations, as you see them here in red triangles, the Dong Bay network, actually installed by a former student of mine in 2004 and pulled out in 2011. So those are available to us. And first of all, to say from the yellow triangle stations, here is an example of a 3-component station and a plot. It's from the station shown here, and the diagram shows the horizontal particle motion when the P wave arrived at this station. So this is confirming evidence that yes, from an openly available station, something did happen at this time of arrival, and the horizontal particle motion had an azimuth that does correctly point back to the North Korea nuclear test site. So confirming evidence. But now I'm going to spend more time on the data from these stations, which are of generally higher quality. And in red, you see recordings of the vertical component of motion. In blue, of the horizontal component of motion. And this is from the problem event. There is a confirming, certainly, seismic event, which must be near the North Korean test site. And the question is, from this data, can we characterize it as truly explosive, or might it be some other type of seismic source? And the key point to note from this data, I'll get into more detail later, is that there are really quite strong shear waves. So the P wave is arriving on the vertical component. On the horizontal component, which are the best measurements to make for characterizing the shear wave, which if they're strong would be typically associated with an earthquake source. So with my colleague David Scharf, using sophisticated measurements of the time of arrival of LG, yes, we can associate this event with the vicinity of the North Korea test site. So as we reached our conclusions in about June this year for presentations at an international meeting in Vienna at CTBTO, confirmation, there was some type of seismic event at about the right time and certainly the right place to match the radionuclide anomalies. And the results I presented so far, if you care to follow up on them, they're on YouTube. But now I want to say what we've done in the last few weeks, largely at Lamont by my colleague Won-Young Kim. So what do we have available to us? We've got the open station. We've got the Dong Bay stations, which are roughly in the same azimuth. We have signals from known nuclear tests at MDJ, and 2 of them were recorded at the Dong Bay network. We've got earthquakes. We've got vigorous, strong mining explosions in this part of North Korea and in this part of North Korea. And we've got quite a few earthquakes, and then there's the weak suspected events, one of them of great interest in May 2010. And as we look at the data from the Dong Bay network, here at one station, 9 and 17 are effectively the same place, we see the P wave and the weak S wave from the first known nuclear explosion of North Korea, 2006. The second nuclear explosion of North Korea, the P wave and the weak S waves of 2009. And then this is the problem event. Something certainly there in May 2010. P wave, well, the ratio of P to S is not the same as in the previous line. And if we go to another station, a nuclear explosion, P and S, P and S, and then the problem event. Quite definitely, the shear waves are stronger than the P waves. At a third station, yes, there's another one. A third component of motion. This is vertical, 3 vertical components for 3 different sources, 3 horizontal components for the same 3 sources, and then for another horizontal component for 3 sources. And the issue is, what is the relative size of their P waves and S waves? And it's a mess. When you look at all the available data, there's all sorts of stations available for short windows of time, sometimes in different frequency bands, and the problem event is the one shown in green, and to the extent that the points are low on this diagram in their y-coordinate, it's more earthquake-like. The squares are from actual explosion data, the circles are from actual earthquake data. So let's try to be systematic about it. And to do that, we've identified 12 definitely explosions shown with let's see, the triangles on this. The explosions are yes, there's the nuclear explosions here, and the triangles, inverted triangles from known mining blasts, large ones. And then in circles are shown 12 earthquakes. So we have a training set of 12 explosions and of 12 earthquakes. And we use now, this is an important part of the discrimination analysis, the data from a combination of the horizontal and vertical. And again, if anything shows high on this diagram, it's more like an explosion. Anything shows low, it's more like an earthquake. And the problem event is in green. But when we apply the classic linear discrimination analysis, I think it was first done for butterflies. You have a butterfly population of one type, butterfly population of another, and you got another butterfly, and you want to know which population is it in. And you develop a set of discriminants, and you find that discriminant that best separates the two populations, and then see how the problem butterfly, which characteristic it is more plausibly in. So in this diagram, that's the same vertical coordinate averaged across frequency. This time the x-coordinate is a measure of the separation from the average d0 across a band of frequencies. So the training set are all these explosions, and for the Dongbei network, absolutely, the known nuclear explosions fall in there. Here's the training set of earthquakes, and the problem event is the one in green, and there's another known earthquake shown here, but the problem event is to us in the earthquake population. So this is my summary statement. Key to our conclusion is the use of a method that deploys all three components of recorded motion, not just the vertical. So this is a very small event. I mean, if we're going to have to do verification so well that we can manage this event's about magnitude 1.5, the level of saying those signal strengths are explosive, which I think they're earthquakes, but if you say it's explosive, we're talking about 1 ton, something like that. Which happens all the time in construction and so on. So tremendous number of events like this arise. So what stations are quiet and reliable that you could use? Whose job is it to build the relevant archives, doing the work of verification down to magnitude levels and corresponding yield levels far lower than had been contemplated when international monitoring assets were developed and managed. And there are so many of events like this. So those are the questions that are now, I think, being asked by the splendid capability that we've achieved. And that's my story.
And it's not about certainty, it's about what level of risk is acceptable. And so uncertainty management is it's a real issue in particular for